Hi, everyone, and welcome back to our last lecture in terms of our whole term. Sorry, I always want to call it a semester of cognitive psychology. I know that the lecture videos have been pretty long. That's usually because we break them up into several days. And like I had said before, it's really a lot of information to condense down into just 10 weeks of content for you. This chapter in particular is rather difficult to parse through in a short amount of time in terms of a single week. There's all sorts of different theories about problem solving and creativity, but for the most part, again, just like with the judgment decision making stuff, I'll just cover the surface level of this literature. That's mainly because there's still a lot to be learned about how we actually problem solve, and there's a lot of variety in terms of human problem solving. And what we find is that humans aren't really that unique when it comes to what we're doing in terms of our problem solving. In fact, a lot of really simple things can solve really complex problems. Um, where we are seemingly unique is our ability to be creative, though. And that creativity aspect is what we'll touch on last in terms of this chapter. So, the learning objectives for this chapter in particular is just to go over some of the general problem solving methods that people use when they're presented with a problem, what a problem actually is in this context, because the more traditional sense of a problem is kind of like I ask you a question versus in the real world, I face problems every day that we don't typically view as problems, mainly because we know how to solve them really quickly. You'll notice that my change of scenery today, or I have a change of scenery today. I'm recording from home. My puppy had a surgery last night, so I have to be babysitting her. I'll see if I can get you a little snapshot of her down there, warming herself by the fireplace. So that's a problem I had to face today was solving how to record a lecture from home and where to do it while maintaining attention on a little pooch to make sure she's not licking stitches or anything like that. Anywho, but we'll talk about how exactly we use information from the past. So again, pulling things out of memory and remember all that architecture and processing that set up the things going into memory in the first place. That's why we cover all that in the beginning of this course, is to really set you up for the end of the course when we're talking about these macro level processes, or like the accumulation of processes that lead to a given output. One of those outputs being problem solving and creativity. So where we really start in terms of problem solving and creativity is this need for creation. Lots of humans, or I should say lots of humans, many humans have this desire to be creative in many different aspects. It's not just the arts. A lot of that desire can be manifested in creation of tools or in terms of games, all sorts of different things that aren't necessarily just the arts related. Mathematicians, especially, I tend to score very high on creativity, believe it or not. And we tend to see that there's a pretty strong relationship between creativity and problem solving. And one of the reasons for this is that problems that are really hard to figure out tend to require a little bit of creativity. But where many of the researchers get interested in this area is trying to identify people who we kind of qualitatively view as creative. So the big C creativity people like Thomas Edison or Da Vinci. I shouldn't have used Edison. Book likes to use Edison. More like Nikola Tesla. Marie Curie is another one. She was extremely creative in solving all sorts of problems when it came to identifying what radiation is. And of course, we have people like Mozart and Bach and all these folks who created all sorts of different art pieces that we can identify at the time that a lot of the art or problems being solved were being solved and created in the same way. And that these folks kind of took a step outside those boxes and figured something out that a lot of other people hadn't at the time. The reason we want to figure these things out, though, is so that we can identify what we can do to be more creative in terms of the problems that everyday people face. Not everyone's trying to, crack the code of the human genome or to write the next big piece in terms of like a musical performance. Some of us just want to get to the end of the day and maintain a living. So it's important for us to identify areas of our lives where we can be a little bit more creative, be a little bit better at problem solving, because as we had demonstrated last chapter, humans are not very good in terms of their ability to make correct decisions. An aspect of that decision making ultimately goes into problem solving. I need to make a decision about the course of action to take when I'm solving a problem. So that's why lots of researchers are interested in this area and what it actually takes to be a good problem solver versus a not so great problem solver. So there are several main methods in which humans uh, know how to problem solve, or that I should say, use to problem solve. So the reason we know this in terms of psychology is because we have access to the insight of the human. We can ask someone, how did they solve this problem? And they can articulate that in language that someone else can understand. There's plenty of comparative psychology research out there, comparative psychology being studying animals, the thought processes of animals, and seeing how they solve problems or make decisions. But by and large, most of us, in terms of the problem solving literature, identify different strategies or methods through asking questions qualitatively. Hey, how did you solve this problem? And then identifying common threads throughout. So some of these problems that people face are really well-defined problems, like I need to go to the store. Wait, what does this one say? I want to go to the store, but Tom borrowed my car. How do I get there? That's a problem. I need to go somewhere. My main mode of transport is gone. Can I figure out a different mode of transport? Hopefully you can just walk. You should have just done that in the first place. But there are things in terms of our task space, or just the space around us, that require our attention and require us to actually come up with a solution. So there's a few examples on here, but all these are examples of problems with it. The main common thread in all these being I have a goal. The goal is really what drives problem solving. If I don't have a goal, I'm not going to solve a problem. So that's where most problem solving stems from, is having a goal. Yeah, maybe I want to have a career in some field. Well, now the problem becomes, how do I get there? In the sense of where I am now, I don't have a career in that field, and I want to have a career in that field. That's the main goal. So these are the types of issues that people face when trying to solve problems. The first type of method that people tend to use, or the more common one that people associate with problem solving, is just a search. So we can think of a problem as a task space or a problem space. And in this problem space, there are steps that lead me to a solution. There might be many solutions. All those solutions can be present in that problem space. And what I need to do is walk through these mentally, walk through these solutions to see if I will solve my problem or if it will help me reach my goal. And this takes time. And as you can imagine, it also takes attentional resources. I need to have knowledge about relationships between things. And as I apply my knowledge in my working memory, I have to serially, and what I mean by that is one at a time, search through these possible solutions until I find a potential solution that will work. So it's not that I will come up with all the perfect solutions right away. It's that my brain will come up with as many solutions as possible. And now I walk through each one until I find one that is satisfactory to me. And like I had said, you must take time to do this. The time it takes is that it's pulling information into your working memory, and as you hold that information in working memory, you check to make sure it will work. In some cases, you might actually try that solution right away. You do a trial and error kind of approach to problem solving. So viewing problem solving as a search is really just like how we would view any type of search. We pull the information, that information being possible solutions or associations, into working memory. And we can demonstrate this, or at least this has been demonstrated, through problem tasks. So like in a lot of problem solving research, we come up with all sorts of creative tasks to test how people are coming up with solutions to problems. And one of these being one based on Lord of the Rings, obviously, of trying to get orcs and hobbits across the river. And you can just read through this if you want, and then start thinking about how you would solve this problem. And if you really want to participate in this aspect of this lecture, I'd highly recommend just pausing the video right now, reading the prompt, and then thinking about how you would solve this prompt. What are you doing in terms of your thought processes to come to the solution that this prompt has? So if you've done that, or hopefully you've unpaused the video at this point, this is how we can think, and maybe this is what you did. Perhaps you didn't do this. Maybe you're very mathematically minded. But you might have done something like this, and in which, stumbling over my words, in which each one of these numerals represents the hobbits and orcs. So this numeral represents the orcs, this numeral represents the hobbits, and then this represents the river, and how many of each are on the other side. And this is our starting space, obviously. It starts with the boat. Well, the boat will be the asterisk. It starts with everyone in the boat on one side of the river. What are the possible solutions or next steps in terms of this problem? Well, what my brain is likely doing is searching through all the possible solutions, seeing if it fits the criteria of the rules that have been set out in the prompt. If I've met a certain goal, or I start moving towards a certain goal, that's great. And that's so the problem space here is thought of as all the possible solutions towards the first step in this problem. How do I take the orcs and the hobbits to the other side of the river while still following the rules? Part of that problem space can also come up with illegal solutions, so things that wouldn't actually work. Obviously, our brain should check these and say, that won't work. I will have to choose something else. But ultimately, this first step is accompanied by all these possible solutions. And there's many more solutions. I'm not going to go over the entire problem for you, but because you can just look it up on the internet. But ultimately, our brain needs to walk through the possible solutions, checking along the way if it would work. And by the time it comes up with the solution, you do this step, this step, this step. That's when your brain has checked mentally. Does this fit the criteria of the prompt? Does the next step fit the criteria of the prompt? And so on and so forth until you found the steps to the solution that you're looking for. This is what we think of as problem solving as a search. And it's not just problems like this. It can be thought of as all sorts of different things. So let's go back to the example of someone's borrowing my car and I need to get to the place I need to get to. Well, what are the possible solutions to this problem? Could I take a bus? Could I walk? Could I call an Uber? Whatever. All possible solutions, and whether they're viable or not is up to me and my brain to decide. Now, of course, sometimes we might choose an incorrect solution. So, especially in real life, when the problem space has many, almost infinite possibilities in terms of steps or places that you can go in terms of your problem space. And when I say problem space, I mean all the possible next steps or next solutions to your problem. But really what we need to do, or what the brain needs to do, is consolidate this information. And one of the ways it does this is first through learning. So once I have figured out a solution to a problem, I am more likely to use that same solution to said problem next time I encounter it. That's one way, that conditioned learning aspect. The other way is some problem solving heuristics our brain has built in to help narrow down the search so that I'm not sifting through every single possible solution. There's things that I know I should just use in terms of information for my solution. And a good example of this is problem. I'm hungry. Now, I'm at home right now, which means the possible solutions to eating, at least if I'm really hungry and want to eat right now, should all be based on the food I have at home. A heuristic here being, is there food present in my pantry or in my fridge that I can eat? And hopefully there is. And if there isn't, then I have another problem. I need to go get food. But these problem solving heuristics help me, the problem solver, narrow my search in terms of possible solutions. First step in terms of I'm hungry is, do I have food at home? I'm not going to think of all the types of food I can eat that I don't have the possibility to make. That would be not very advantageous for me to do. One of our one of our heuristics in terms of general problem solving is something called a hill climbing strategy, which is kind of an analogy for how we approach problems in a stepwise fashion. So I only choose solutions that help move me towards a goal. So we can think of my problem as a hill to climb, and I'm only going to choose solutions that help advance me up the hill. I'm not going to choose solutions that take me downwards down the hill. The problem here is that in some cases we might need to go backwards or move away from our problem for a little bit. Now, what I mean by this is that the step itself seems counterintuitive. I shouldn't want to move in this direction. It's actually moving me away from my goal. And this is when we start to run into a few problems. When our brain sees this, in terms of it interprets us moving away from the goal, whatever goal that might be, I think I'm using a wrong strategy. I'm going the wrong way. So I'll probably abandon that solution and try a different solution. So when we use a hill climbing strategy, we're only taking steps that move us towards a goal. And again, this is a really good heuristic to use because for the most part, things that are moving us towards the goal are going to help us find a solution to whatever problem we have. But again, not every problem in real life requires us to constantly be more moving towards the solution of that problem. Sometimes we have to take a little bit zigzaggy of a path to get there. An example of this being something like going to college. My goal is to graduate. Well, if I really wanted to graduate, I'd be taking as many classes as possible. I'd always be studying. These would be things that would be constantly moving me towards a goal. But that's unrealistic. I need to eat. I need to sleep. These are things that would take me away from that goal. Obviously, I can't study while I'm sleeping or eating. In fact, I'd probably need money to sleep and eat, so I'd probably have to get a job too. These are also things that are going to move me away from that goal. So it's not always the best strategy to use a hill climbing approach in terms of my problem solving ability. Another good example of where the hill climbing approach might lead you astray is even that orc and hobbit problem that we had just talked about. In some cases, the easiest solution to this is going to require me to move orcs back across the river to the wrong side of where I don't want them to be. That's the only way to move the hobbits all the way across first. So that step is going to seem pretty unappealing to my brain because I am going the wrong way. I'm taking things away from the direction that I'm supposed to be taking them. So it's important to remember these heuristics are good in a lot of situations. They help ease our our mental load in terms of problem solving and decision making, but at the same time, they can lead us astray when we need to think more critically or to do things like this, which would be go the other direction, do things that seem counterintuitive. Likewise, our brain does a means ends analysis, which means it makes a choice at the start of the problem when I'm presented with something. And that choice is, do I have the means to actually solve this problem? Unfortunately, a lot of folks tend to view math in this way. So when they're presented with a math problem, their intuitive thought is, I don't have the math ability, the means to solve this problem, so I'm going to abandon it without actually thinking about whether they can solve the problem or not. So lots of word problems get abandoned very quickly in terms of people who aren't comfortable with math versus people who are comfortable with math. This is just another example of a type of heuristic our brain is going to use very, very quickly. I have math ability. I don't have math ability. I see math in this problem. Not for me. And it goes far beyond math, too. So let's use the food example again. Maybe I'm super hungry and I feel or I don't know how to cook. Well, now if I don't have any food that is ready to be eaten, there's no way I can solve my problem of hunger. Now I need to go do something else. So, just these are really simplistic examples, but at the end of the day, lots of our problems that we have to solve aren't as easily called into the focus of attention like this in terms of whether we have the means to solve them or not. In a lot of cases, we might actually have the means and not realize we have the means. Here's another prompt I want you to go through. Take a minute, read the prompt, see if you can solve the prompt, and then we'll talk about why I'm bringing this prompt up. So this is a good example of what might happen in a means-ends heuristic approach to problem solving. Some of us might just approach this problem in terms of, do I have the actual means to solve the problem? Every step of the way here challenges, do I have the means? So what's the difference between what I have and what I want? Well, it's distance. Do I have the means to cover that distance? I have an automobile, but it doesn't work right now. What would help make it work? A new problem arises. Do I have the means to solve that problem? And so on and so forth. So this is an example of how our problem solving can be complicated in terms of heuristics. We start thinking about each step of the problem through this heuristic lens. And if we can solve, we get to a point where I can solve one of the problems, then I can start solving the others. Again, this is not a good or bad. I'm not trying to advocate for this heuristic or not. It's just a way that our brain approaches these problems. And obviously, the thinking about this happens very quickly. So it's not that you have to sit there and cognizantly go through each one of these steps. It's that your brain is doing this very rapidly, very quickly, and often without your knowledge or awareness, I should say. So that when you do get the prompt, I need to take my son to nursery school, all these steps, if there's a challenge, are basically approached instantaneously, very rapidly, until I get to the hang up of what's going on. It'd probably be right around my car not working. But there's another way that we can approach problems, especially when it comes to word problems or abstract problems, and that's through pictures and diagrams. Remember, an aspect of our working memory is that visual spatial sketchpad, the ability to visualize things within the focus of attention, even when they're not there. And one of those things can be the conceptualization of the problem itself. Here's another prompt, another problem that is used in lots of problem solving literature. So go ahead, pause the video, read the prompt, see if you can come up with a solution to this prompt, and then think about what you did, and I kind of primed you to do this already, in terms of solving the problem. So hopefully you did that, and hopefully you came up with, I honestly don't know the solution off the top of my head, and I can't see it on my computer screen, so I can't tell you. Hopefully you got the right answer. But the trick of this problem is you don't count the A volume and you don't count the Z volume. And the reason is, if you think about where the bookworm is, the bookworm is on this front cover of the book of A, so he doesn't need to go through volume A. Likewise, the back cover is back here. So volume Z down here, their back cover is going to be touching volume Y. So when the bookworm gets through volume Y, they're going to hit the back cover of volume Z. So in this problem, when you're doing the math to solve the problem, you're only using volumes B through Y and not A and Z. You use 24 instead of the 26 letters of the alphabet. And one way that people can get primed to do better in this problem or solve it more quickly and accurately is by asking them to visualize where the bookworm is starting in terms of the books on the shelf. And being able to visualize that helps immensely in terms of people's ability to solve this problem. In fact, I believe, and I think the book has the actual numbers, it's right around 65 or 70% of people will accurately solve that problem when they're told to visualize the problem. Now, one way in which we visualize and one way in which we help to conceptualize things in general is to pull things from our long-term memory. Remember, it's super important in terms of storing information that we can use it at some point in the future. One of those times is approaching problems in which that information is useful. Otherwise, why would we store all these memories? And most people can and do use these hill climbing strategies and means ends analysis to initially sift through many different possible solutions. But our experience and our memory helps consolidate that even further. It helps identify various aspects of both the hill climb approach and the means analysis, ends analysis, to identify or even downplay some of these heuristics. Let's say I've approached a problem before that I felt like I couldn't do, but someone showed me a possible solution or I figured it out eventually. And now I'm presented with a similar problem that I think I can't solve. Well, now I've chipped away at that heuristic. Maybe I can solve this. Maybe I'll do something else in terms of my problem solving to figure out a possible solution. So the ability to use past information is super important when it comes to our problem solving. If we couldn't do that, or we couldn't pull things from working or long-term memory into working memory, we'd have a lot of trouble actually navigating the environment and solving problems. So one of the ways in which we approach problems in terms of the current problem is similar but different from something I've seen before is through analogy. You're going to get presented a lot of problems today, and I hope you're sitting here and trying to. A lot of them are just kind of like riddles or math problems, but they're really important to think about how you're approaching this problem. This one is used in quite a bit of literature because it's a pretty big effect size when we do see what happens. So again, pause the video, read through this problem, then unpause the video when you think you have a solution. So hopefully you did that. Hopefully you think you have a solution. Maybe even just write the solution down because you're going to have to, or you could, read another prompt here. And if you read the chapter before this, maybe you've already been primed. There's a story that's presented to some participants prior to doing that problem. It's called the Dictator Fortress problem. Where the problem is, you can't just directly attack the fortress. You need to attack from many sides all at once so that your combined forces all converge on the same spot while not being detected um, by the fortress guards or whatever. I honestly haven't read this prompt in a while, but the main reason the prompt is given to people and people are asked, and they're not even told that it has any relationship with the tumor problem prior to this. People who are presented with this prompt and then presented the tumor problem are far more likely, to a very significant degree, to solve the tumor problem more quickly, more accurately. And that this hint, so the hint of the dictator and the fortress story, is priming them to think about the problem in a different way. They start using an analogy. Oh, I see the fortress as the tumor. And I want to get the guards or the soldiers to the fortress all at once. But how do I do that without being detected? Well, I need to send different soldiers from different sides all at once. And the solution to the tumor problem is obviously I use many different light rays from all different angles so that it doesn't damage any of the tissue, but all the light rays converge on the tumor and hopefully destroy the tumor. Now, this is what I had just been talking about. The analogous problem is provided, or the fortress and dictator problem is provided, but we don't tell them it's related to the tumor problem at all. And you still see pretty much a 2 to 3-fold increase in the ability to solve the problem, solve the tumor problem, after being presented that problem first. We don't tell you it's related, we don't say anything else. Now, you can suggest that, hey, this might help you with the tumor problem. Think about it this way. And what happens is that basically most people solve the tumor problem when you provide them with that story first. And you tell them that it might be useful in the future. So even just a little suggestion on, hey, you might want to use this as an analogy for solving the next problem can greatly benefit people. And in terms of our problem solving, that suggests that we're really good at using past experience to base our current solutions on past experience, even when it's completely unrelated or seemingly unrelated. The problem is this unstructured use where like no one's helping you map this out is very rare. It's pretty hard to do because it requires thinking about the problem in a more abstract way. And that abstract way requires lots of in-depth thought on not just possible solutions to the problem, but the rules of the problem itself in terms of what are the latent structures of this problem, what are the latent rules. So in the tumor and fortress example, the latent rules are whatever I'm trying to get to the target cannot come all in one batch. And what needs to happen is that I need to give small doses, or small bits need to come in, not through the same area. That's a latent structure, something that applies to both. But again, it's really hard to think about past stories or events that happen to you that can work as an analogy in the moment, because it requires thinking about that and then identifying that, hey, this is similar to something else I've seen. But really, what's going to happen is that something like, because this does happen naturally, when you do identify the latent structures of a given problem, sometimes you will cue in on a past experience that is helpful to you and that you can use as an analogy for solving the current problem. Now, there's a few different strategies that can make analogy use more likely. The first is when I'm first learning something in terms of my past experience, trying to relate it to other things. I've covered this before in terms of the memory chapter. The more in-depth or neural networks you build in terms of our semantic networks, the more likely that information is to be recalled by happenstance, and these free associations are more likely to occur when I'm thinking about things relationally. How does this stimulus relate to this other stimulus? Now, the other strategy that can help analogy be used more likely in terms of our problem solving is priming system 2 thought. Remember, in our last chapter, I had talked about system 1 versus system 2 approaches to our thinking. System 1 being this more automatic, heuristic based thinking, which is pretty much default in most organisms to include humans. We need to prime ourselves to think critically, think about the relational aspects and these deep analytic aspects of the problem. That can help us to draw more conclusions, to draw more relations to other problems that we've encountered before and solved. And in doing so, when we encounter a new problem that fits some of those criteria, we start recalling those things into the focus of attention a little bit more easier, such that we can use those as analogies to the current problem. One example of where this becomes very obvious is in something called expertise. There's a whole area of psychology or cognitive psychology that just deals with expertise, in which you present problems to an expert of the field and a novice of the field, so someone who's just starting out. Many of the times that we do this, novices will take longer. They'll approach problems far more superficially, meaning they just use the surface levels of like the rules of the problem, the actual information provided in the problem. Whereas experts will use a lot of heuristic decision making, but these heuristics are all based on their past experience with these types of problems. And lo and behold, if you're an expert in an area, you've had lots of experience with a particular type of problem that helps you relate that information far more easier, which ultimately means that experts are going to be way more likely to use analogies to solve problems. That helps them solve them quickly, that helps them solve them more accurately. In one particular study, they gave engineering students, the expert students versus the novice students, a particular engineering problem, asked to discuss it. The expert students were generating types of analogies at a far higher rate than the novice students. So they were saying things like, oh, it's like this other problem that I've encountered. It's like this other problem that I've encountered. Or it's like this other thing that, a lot of people have encountered. It's a very famous saying when it comes to expertise. The best way to know if someone's an expert is if they can explain their field to a 5-year-old. And the best way to explain things to a 5-year-old is to use analogies. If you can't use analogies, you're probably not as much of an expert in that field as you think you are. Use of analogies requires all that relational learning, the latent structures of the things you're talking about. Being able to relate those things to someone who has no knowledge is an incredible feat when it comes to problem solving. That is a problem in itself. How do I convey really complex information to someone who has no knowledge of the topic? Another way in which we can address some of our problem solving is to break the problem up into its sub goals. We might have a current goal, but we need to break it up into its sub goals to more easily manage it. So I'm going to use the example again of going to school or going to university in order to get a degree. That's a pretty big goal. And yes, you could approach that problem all at once and do it all at once. But it's not going to be very effective to think about the problem in that way. In fact, people who do think about going to school in that way tend to burn out a lot faster. They tend to not get as good of grades. And ultimately, they don't tend to actually follow through with the problem as much as someone who breaks up that problem into its sub goals, or that goal into its sub goals. Likewise, you can break those sub goals up into further sub goals. So things like passing a class is going to help me get a degree. Well, what do I need to do to pass that class? I need to do all the assignments. Well, let's take a given assignment. What do I need to do to accomplish that assignment? Is there ways that I can break this up into smaller components? And by breaking them up into smaller components, the smaller components usually have easier solutions than the overall problem. And what we find in terms of the research is that experts are really good, at least experts in whatever area they're in, are really good at breaking up a problem in their field down to its most micro level sub goals so that I can tackle a sub goal one at a time. It's easier to manage mentally. It makes me feel more accomplished. Think about that hill climbing approach. If I can break these, or that hill climbing heuristic, if I can break a goal up into its many, many, many sub goals, each sub goal is another check on moving me towards that overall goal. That feels really good. That's highly motivating. So experts tend to do this. And experts ultimately tend to have a lot of these sub goals almost automized to the point of basically a flow chart. And I know I have a stupid, silly meme over here, but this is ultimately what your brain builds architecture-wise in your cognition. Really simple logic gates. Do I need to do this or this to move me to my sub-goal? Or to complete a sub-goal? This is the sub-goal. Does it move? Yes or no? And so on and so forth. That is ultimately what breaking up the overall goal and breaking up that problem. How do I reach my goal? In breaking it up into its sub goals, super important. That will help you not just in this class in terms of thinking about thinking, but in terms of real life. How do I approach a problem in real life? Well, ultimately, I should try and break it up into its most simple components. You don't need to be an expert to do this. However, being an expert helps you to do this because you've identified or you've had this experience where you know you can take certain steps that get you closer to your overall goal. A really good example of this is how people memorize chessboards. So there's plenty of folks out there who are experts in chess, obviously. When presented with the problem of remember this position on the chessboard of all the pieces, experts tend to chunk the board into various quadrants and remember the organization of the quadrants. That helps them remember the actual organization of the board. They bring back, I think it's like 5 to 10 minutes later, and they say, okay, put the pieces on the board just the way you saw them. And what you're seeing here is in the cross-hatching is where mistakes were made. Sometimes the expert will make a mistake here, but it's very rare. Unlike the typical average person's performance on this task, who tries to memorize everything at once. The goal being, I need to memorize the entire chessboard. I don't break it up into sub-goal components. I'd rather just memorize everything at one time. And what we find is that, of course, this is just too much information to actually try and memorize, so you make many errors in terms of what the board looked like. Now, this is an important point in terms of what I need to bring up next. Because I've been talking about breaking up the problem into its sub-goals, or breaking up the goal into its sub-goals, and that's how you truly solve the problem better. But to understand the problem, you need to first define it, in the sense that there are two types of problems. One that you can very concretely lay out, and one that you can't really concretely lay out. One that doesn't have perfect solutions or paths to those solutions. And this is a whole line of work in terms of how people approach these two types of problems. But in terms of the definitions surrounding this, there are ill-defined problems and there are well-defined problems. And they are exactly how you think they sound. Ill-defined problems represent problems that don't have clear goals. the solution paths are not explicit. There really aren't expected solutions to these problems. These are kind of up in the air problems that maybe humanity has not tackled yet, or that maybe you as a person have not tackled yet. But at the end of the day, there are no right or wrong answers, so it's a little bit harder to come up with a solution. An example of this would be like, what is morally good? What does it mean to be a good person? That's a really ill-defined problem. We can't really set out the correct solutions to that without first defining what good means and all sorts of philosophical things that aren't super important to a cognitive psychology class. However, a well-defined problem does have specific goals. There are really clear goals and sub-goals that I can point out in a well-defined problem. The example I've been given in terms of graduating or passing or going to college, that's a really well-defined problem. There are steps I need to take to pass and graduate. In fact, your course catalog, or what is that called? Your program of study lays out your course requirements for your degree. In terms of, you need to do these courses, you need to do these courses, you need however many electives. Those are really well-defined goals. I know what I need to do. So that's the general difference between ill-defined problems and well-defined problems. As you can imagine, ill-defined problems have a little bit harder of a time getting solved than well-defined problems. With that being said, sometimes we run into issues with well-defined problems. I can give folks well-defined problems, and they can run into a problem of functional fixedness. So our brain is super good at, again, building associations between objects and the environment and things like their uses. And one of the quintessential examples of this is something called functional fixedness. This was first proposed by when Dunker had a problem which he gave to students. He gave them a box of tacks, a candle, and a match, and he says, okay, get this candle on the wall so that there is no wax dripping on the floor when you light it. Now, most students really struggle, not students, but most of the participants in his task really struggled with this problem because of functional fixedness. And the reason is that the functional fixedness of all the items here, in terms of what each item is and how it relates to the environment, is set in stone. We start using our schemas rather than thinking about the actual ways in which we approach this problem. What are the possible uses for these problems? This is a little bit different of an example here, but by and large the same. I need to get the candle on the wall. How do I do that? Well, I just don't know. There's matches, there's tacks. I can't tack the candle to the wall because then it would drip onto the floor. But the correct solution to this is you tack the box. You would dump out the tacks, or the box of tacks, and then you tack the box of the tack. Tack the tack box to the wall and put the candle on the tack box or in the tack box, however you want to do it, such that the tack box is going to be catching the wax. So when you present the problem in this initial state of, here's a box of tacks, here's a match, here's the candle, you got to get it on the wall without it dripping on the floor. When you light it, lots of people view the box of tacks as a box that holds tacks. There's that functional fixedness, the function of this box to hold things. And right now it's holding tacks, so it can't hold anything else. There was nothing in that prompt that told you couldn't dump out all the tacks and use the box to hold the candle. Now, that being said, when you present this problem with all the tacks already on the table, more people solve this problem. So what is going on is we have this bias. When we see things, we are relating them to their function. When we see the box of tacks, and it's filled with tax, we see it as a holder for tax. It's really hard to override that and say, oh no, this should be holding the candle. So this functional fixedness is something that we really get hung up on in terms of our current problem solving. When I need to pull in tools or use information about these tools towards a possible solution, often I'm going to use them or view them the way they were intended to be used and not tend to think about all the possible uses for that thing. So I'll circle back to that in a minute when we start talking about creativity. But another way in which this is presented is something, a German word called Instellung, which is a problem-solving set. This problem-solving set is the possible things that I can use to solve the problem. And this is just a belief that I have. It's not the actual things that I have to use to solve the problem. These are the actual what is available to me cognitively in terms of my beliefs, my strategies, my preconceived notions about how things relate to other things. The Entstellung is something that I have that I've learned to use. So it's my belief about what a box of tacks is for. It's my belief about how to stop candle wax dripping onto the floor. And these beliefs can obviously be malleable and change over time, but ultimately they bias our current problem solving because it's what I truly believe to be, the use for a tool or the possible solution to something that will bias how I'm approaching the problem altogether. So a quintessential example of this is you have 4 buckets, you know the volume of 3 of the buckets, but ultimately in this bucket with no information about it, it's just an ill-defined bucket, you want to put 5 ounces of water in that bucket. And you have an unlimited amount of water. Well, how do you get exactly 5 ounces of the water into that ill-defined bucket? So if you really want to do the problem, I know the solution is already kind of here. Go ahead and think about it. So hopefully you thought about it. Maybe you pause the video. Ultimately, what you do is you fill up this one and you start dumping water out because these volumes will eventually get you down to 5 ounces. These are all in ounces, by the way. I should have said that. But you'd pour 10 ounces into here. That gets you down to 33. You'd pour this water out on the ground or wherever. You'd pour another 10 ounces into there. That'd get you down to 23. And then you'd pour 18 ounces into the purple one. And what you'd be left over with would be 5 ounces of water. But a lot of people don't tend to do this because I keep butchering this word. I took German at one point in my life and I could speak German, so I should know how to speak this well. Anywho, the Einstellung is the notion that I probably should be pouring things in to the bucket rather than pouring things out. A lot of the times we don't tend to think about the problem in that way because that's not intuitive. That's not what I've grown up or experienced in life. What I've learned in life is that when I need to measure something, usually I'm pouring it in. I'm not pouring out. Another example of this is when we really get asked to think outside the box. So I actually used this one in my master's thesis when I did lots of insight problems and working memory research in my master's program. And I used this task to see how quickly people could solve the problem. And the problem is you need to draw 4 straight lines through all 9 dots without lifting up your pencil or pen or whatever it was. And if you want, you can draw this out on a piece of paper as long as they're mostly equidistant from each other and try to solve this problem. So go ahead and pause right now, try and solve the problem, and hopefully you've unpaused at this point. I'll show you the correct solution to this problem. So you can start at any corner, you go down, and you go out, then you go here. I'm drawing with a mouse pad, so it's a little bit hard for me to do. These are straight lines, by the way. And there you go. 4 somewhat straight lines on the mouse pad, but I didn't have to pick my pencil up nonetheless. Now, most folks aren't going to think like this. In fact, they're going to think in the sense that I need to do this all within this little box here. Is it possible? And the answer is no, it's not actually possible to draw the 4 straight lines within that tiny little box. So trying to attempt this would be very, very difficult to do. And in fact, many people do the trial and error method here. They start drawing lines, erasing them, gradually figuring out that I need to do something different than approach the problem the way I'm approaching it. And that's where we start getting that outside the box thinking. How do I break down some of the rules that I've imposed on the problem myself? There are no rules saying you can't go outside these 4 dots. You just need to draw 4 lines. Nonetheless, people self-impose this problem on the task. So the problem-solving sets, or these beliefs that we have about problems and the rules surrounding problems, can really hold us back in terms of how we approach a problem set. Now, with that being said, it's not necessarily a bad thing. We don't want to be sitting there doing a bunch of strategies that aren't going to work in the long run. We don't want to be taking chances or doing things in terms of our problems that are ultimately going to lead to failure. That's why we tend to bias our problem solving on past experience, things that have already worked. Now, the downside of that is when we are presented with a problem that requires us to think outside the box, then we start running into issues. Now we're going to be stuck, again, with that like functional fixedness on specific objects, or it's another term for functional fixedness, that Entstehung, on the belief surrounding a problem. I believe there's particular rules surrounding this problem, so I operate as if those were true, even though they're not. And sometimes that will blind me to possible solutions because I don't pay attention to those possible solutions. And ultimately, that's where we get into creativity. The ability to break away from these set in stone beliefs or problem sets that we have experience with, or a lot of experience with. But creativity itself is not very well defined in terms of cognitive psychology. Creativity can apply to things like generating something brand new without a particular problem. But often we frame this in cognitive psychology as the ability to draw associations between things that are completely unrelated. So when we talk about creativity in terms of the cognitive end of things, we tend to focus on what we can actually measure. Now, being creative is not just being random either. Being creative is finding unique solutions to things like problems that don't have a very good answer. And we have plenty of case studies of creativity. So people that we can qualitatively say, this person was very creative in their field. Okay, well, what are those things that they had that made them so creative? What is something that Einstein did that made him so creative in the field of physics? Well, he started thinking about problems in a different way than everyone else was approaching these problems. Now, there's certain personality traits associated with a lot of these creative types. Things like a willingness to take risk, maybe a dampened response to negative feedback. But ultimately, there's not a lot of well-defined overlap between certain folks who are creative in one field versus another. Often, a lot of this just becomes luck. So I have just happened to be creative and it just happened to work. One of the kind of downsides of this is that any specific individual might be viewed as creative, but there might be, hundreds of equally creative and equally intelligent folks out there that never had that opportunity that would have been just as creative as someone like Einstein or Tesla or Marie Curie, who never got the chance. So this is something that, in terms of like evolutionary psychology, we view creativity as almost the abstract genes of our thoughts, things that are just random mutations where someone thinks way differently than everyone else. In a lot of cases, that's not going to be very advantageous. So that person's going to, fall to the wayside. People don't like how they think. They are ostracized. In other cases, they think of something fairly good and we praise them. We view them as super creative, super intelligent. Now, all this is great and all, but we do have something in all of us that allows us to be creative. We can identify the different stages of creativity. When we're presented with a problem that we have never experienced before and it's not similar to anything that we've seen before, maybe some of the riddles that you've been presented with today were things that you had never seen before, and you don't have any way to solve these offhand in terms of past experience or analogies or decision heuristics. So you need to be creative in terms of identifying where you can connect the dots to some of your past experiences. Now, studies as early as the late 1920s we're looking at how do we measure creativity in people. And actually, one of the more prominent theories on creativity that still persists today is this four-stage model that Wallace had proposed. And that's that people initially gather information. This is the preparation phase. Then you incubate that information. Essentially, you take a break from it. You let it sit in your mind, just kind of stewing. And then there's this moment of insight, this illumination, this aha, I figured it out, even though you weren't the one doing the work. Your brain was. And it was all behind the scenes, unconsciously. What happens consciously after that aha moment is the verification. Now I confirm, either logically thinking through the process or just simply doing whatever solution I thought was the solution. What is ultimately the more interesting aspect of the four-stage approach to creativity is this moment of illumination. So this insight that I have. Now we can view insight in many different species, not even just humans. Some of the more early research done on insight was actually done with chimps, where we left lots of tools, what we view as tools because we've probably used them before, in their pen and presented them with a problem. There was a banana suspended in the middle of their pen. These chimps had presumably never used the boxes before to build up a ladder to get the banana. Nonetheless, they, after a while, would look at the boxes, they'd manipulate them, they'd kind of just not do anything with the boxes for a while, but then suddenly you'd see a chimp walk over to the box, bring it over towards the banana, and stand on it and start looking up. And then that starts that connection. Oh, I can, and presumably this happened before they stood on the box, was, oh, maybe I can stand on this thing over here that I can move, and I'll be higher in the air. There's a moment of insight. And I'm sure you've experienced this at all sorts of points in your life where you were presented with a problem, you were thinking about it really hard, and you were just stuck on it, and you went to sleep, and then the next morning you woke up and you're like, I got it. I have the solution. We're not really sure why this happens. There's all sorts of theories proposing what's going on consciously and unconsciously in terms of the associations being made, but ultimately it's just creativity. There's an aspect of our cognition that is working on these problems or making associations between different aspects of the problem that lead to this moment of illumination, what we call insight. Now, we can actually measure insight both subjectively and objectively. One of the subjective ways is having people work through problems. So again, if you want to do these problems, pause the video right now and think about how you'd approach these. I gotta find my pointer here. And ultimately, we keep asking them every 10 seconds, give a rating of how warm you are. So like the classic warmer, colder feeling. How warm you are in terms of the correct solution from 0 to 10. And ultimately what we find, so we work backwards from these measurements. So you just keep asking them every 10 seconds, press the button on how confident or how close you are in warmthness to the solution for each one of these problems. And what we find is that when people find the correct solution, they tend to rate their warmth as really low. Except for there's a 10-second before I have the solution, I suddenly jump up to the solution. Whereas if I come up with the incorrect solution, I tend to view my solution as more warm, or I'm feeling more warm with my solution at a more gradual rate. So I tend to be working on it incrementally. And not so much where I'm not feeling very confident, suddenly, yes, I have the solution. So once they have the solution, you can have the 3 data points back, again, because you're measuring constantly every 10 seconds. Likewise, we can see neural responses in terms of a dip in our NI. This is the NI area is right here on your parietal lobe. The electrodermal activity in that area. We have this big decrease shortly before I give a response. So this right here, this really rapid decrease, is letting us know that something is going on. And like the R right here, that is when they give their response. I have the solution. I know what the answer is. Bingo, bango. Whereas in the incorrect solution, I don't have this really sharp downwards or initial negativity prior to my actual response. And then afterwards, I still have this very large discrepancy between the incorrect and the correct spaces of my brain activity. So again, more so on the parietal lobe here. But this is just a neurophysiological measure demonstrating that we are coming up with a solution or something is going on behind the scenes prior to conscious awareness of the solution being formulated. And this incubation kind of feels like, I know the meme is kind of weird here, but it feels like this, where if we consciously think through the problem space, it takes us a lot longer. Whereas the insight that, I have the solution, seems to happen like this. I have these 2 places I want to be, and I just jumped. I went from this to this really quickly, at the drop of a hat almost. But obviously, there's a little bit of argument here. Is the brain actually working on these things behind the scenes? That would seem very economical in terms of how things are happening. Also, people don't like to tend to think that they have little to no control of their thought processes, mainly because if it's possible for my brain to solve very complex problems without my conscious awareness, what do I need my conscious awareness for? This is one of the last pegs for conscious awareness. We don't need it for learning. We don't necessarily need it for memory. We don't need it for attention. So what good is it doing? Lots of people have very strong opinions about, well, it must be for solving problems. And if the incubation folks are right or the insight folks are right, you don't even need it for that. So this is just another area where we have lots of mixed results as to whether people are working on these problems or not. And again, because we can't actually monitor whether people are working on a problem when we're distracting them or telling them not to think about something, it leaves a lot to be desired scientifically. So lots of shaky ground in terms of insight and incubation here. Most of the time, we tend to think of incubation and insight mostly as mind wandering. So I get bored because I'm not coming up with the solution. So I let my mind wander, seeing if any of these um, attentional demands can be broken down. Where I'm hyper focused, I'm really focusing on specific nodes within my semantic representations of this problem. When I let my mind wander, my attention kind of expands a bit. And now I'm getting more of that spreading activation where I might draw into the focus of attention really completely unrelated things or seemingly unrelated things. And now I can use that for the problem itself. Where when I was hyper focused, I might not have done that. I might have filtered that information out because I didn't think it was relevant. So many of this, or much of the incubation literature, again, it's hard to define in terms of, are you actually mind wandering? Are you actually not thinking about something? Or is it just a degree of attention to particular elements? You can think of that aha moment not as I'm not paying attention to these elements, but I am at such a high level or at a wide level that I'm barely paying attention to any of them. But once I've made the connection, it feels like it came out of nowhere. So this is just another way in which we think about incubation and insight. Much of the research in this area involves like word-based riddles and visual-based riddles like this. So how long it takes someone to get these riddles. Let's see if I can do these. I did not look at the answers beforehand, so it's going to be really hard. You're going to see incubation in real time. Although I am pretty familiar with this. So if you don't want to hear the answers yet, I'd say pause the video, try and get through these. The first one obviously being really easy. That's reading between the lines. I believe this one is probably split second timing. Yes, it is. This one, search over and under. So search over, or oh no, I'm wrong on that one. See, coming up with the wrong problem or the wrong solution, really easy and it feels good right away. This is searching high and low, as in search high and low. This one is a hole in one. The word hole is sandwiched in one. Obviously, this one's Jack in the Box. And then this would be double or nothing. So a few problems you present to people until they get the correct solution. Like I just demonstrated, sometimes people will come up with many incorrect solutions prior to them having that aha moment of, yeah, that was the actual right solution. I kind of cheated because I have seen these so many times in my life that I knew many of the answers kind of based on memory. Now, there's another way in which we measure creativity. Not so much the incubation stuff, how long it takes you to come up with a really unique solution, but in terms of your ability to think divergently and convergently. So, convergent thinking is the ability to bring in associations where it doesn't seem like there are associations. The way we measure this is through something called the remote association test. In this test, we give participants 3 words and we ask them to generate a 4th word. In some cases, the 4th word is just added before or after each one of those 3 words. In some cases, that word is just related to all 3 words. But regardless, the ability to do this quickly and accurately reflects your creativity. So they might see something like this example down here. You have cookies, 16, and heart. The answer to this one is sweet. Cookies are sweet. Sweet is part of the phrase of Sweet 16, and then you would use sweet in the word sweetheart. So this is just one, and there are some cases, many different words that will fit here. The nature of the fit depends on how creative you are. So you can use something like just the words before and after these things. That might take you a little bit longer with this one. I've honestly no idea if that would work, but thinking outside the box in terms of how do I connect all three of these words? So let's try a couple. It's always a fun task to do. Go ahead and see if you can come up with the fourth word for each one of these. And you can pause the video now. Hopefully you did. Now, hopefully you won't pause the video and you just start sitting there staring at the screen. The answers to these, at least the most common answers, are jack, grade or high, box, party, and nut. So I think the more difficult one is actually the fifth one here, where nut is a synonym for a madman. The acorn is a nut, and then you have the actual tool that of a nut that goes with a bolt. So that is some examples from the remote association task, and basically we're measuring how quickly you come up with this fourth word and how accurate you are in terms of coming up with that fourth word. Remember, lots of things in cognitive psychology all come down to reaction times and accuracy. So even this really complex thing, like how creative are you, can be reduced down to something simple like this. You'd have participants do all sorts of these, like 40 different trials to see how quickly they're coming up with that fourth word. Now, on the flip side of this, in terms of our creativity, is divergent thinking. And that's an ability to come up with novel solutions or take the problem in an unanticipated direction. This one gets a little bit more qualitative in terms of our measurement. Ultimately, we measure how many of these things you come up with. So these are just two examples of divergent thinking tasks. The quintessential example is how many uses of a brick are there. We score this based on how many unique cases of a brick. So, like saying I can build a school, I can build a building, I can build a house. Those are all just considered one. It's building material. But ultimately, we're measuring how many unique things you can come up with for a brick. And there's all sorts of different things that you can do this. You can ask people to organize information a different way, but the nature in which they can think differently than the intended use for these things is considered divergent thinking. How many different things? Now, whereas convergent thinking was thinking about the relations between things, divergent thinking is thinking about how different things can be, even when it's just the same thing. I know that sounds a little weird, but that's really what it is. So ultimately, the nature of creativity, or creativity itself, is the culmination of both divergent thinking and convergent thinking. And another aspect, something called forward flow. And that's how much of our current thinking about a problem breaks away from those past thoughts. Forward flow wants to integrate some of that past thought, but really take it in a different direction. And the more different you are in terms of that forward flow, and the more associations you can make in your convergent thinking, and the more divergent thinking you can use in terms of the novel aspects of a problem, are going to be related to how creative you are. So I have, I just pulled a few images off the internet of people using tools in unintended ways. That's an example, again, of divergent thinking. But again, there's aspects of this of convergent thinking as well. So especially this one. I don't know if you've ever been in a situation like this, and I hope not, but I have done something like this before. I had cooked things on a coffee maker in a hotel room because they didn't provide me with a microwave, and I'm cheap. So this is an example of both divergent thinking, divergent being how do I use the coffee maker differently, but also convergent thinking. I know coffee makers produce heat. I need heat to cook material. So again, how much of this in terms of my creativity, my ability to be unique in terms of solving problems comes down to all three of these aspects being used together. And again, you can use more or less of one to come up with really creative solutions, but ultimately you need to exercise this. Too much of the basis on past experience is going to lead you to that realm of functional fixedness in pretty much every aspect of your life. And it's not just tools, remember. It is beliefs, it's thought patterns, all these things that get stored in long term memory that you're attending to that are biasing your attention. All these things ultimately are going to lead you to be less creative, less able to solve really complex problems. And that's the last lecture. That's the last slide of the last lecture in cognitive psychology. I hope you had a good time in this class. I know it's not my favorite way to teach this class, and if you've watched all the way through these videos, Godspeed, because I know I've made several of them very long. Um, but there's just so much content to cover in terms of a 10-week course, and if any aspects of this course have interested you in any way, I'd highly encourage you to dive deeper into that aspect. Look up the literature, look up some of the review papers surrounding different theories or phenomena within that realm. There's so much there that I can't cover in the span of 10 weeks, and definitely not in an online class. Thank you all for being such great students in terms of both the discussion posts. You've been doing excellent in your write-ups and doing your statistical analyses and asking really interesting questions over the course of the semester. So I hope you all enjoyed this course, and I will not see you next time. Have a good day.